Okay, so for this problem we have a joint probability density function, y times e to the minus x, where y must be less than y must be between 0 and x must be positive. First part of the question is to find the conditional distribution of y, given that capital X is equal to x, and then to find the conditional distribution of x, given that capital Y equals y. So first off, let's find the conditional distribution of y, given that capital X equals x. So the capital distribution of y, that'll be the joint distribution divided by the marginal density of x. Okay, so first things first, let's figure out the marginal density for x. And before we get too far into this, let's go ahead and graph the region where this is defined. So this is the line y equals x, and the y-coordinate must be between 0 and x, and so what I'm integrating over is going to be this region here. So if I find the marginal density for x, that means that I fix my x-coordinate, and the y-coordinate must be between y equals 0 and y equals x. So the marginal density will be integral from 0 to x of y times e to the minus x dy. So doing the integral, we get y squared over 2 times e to the minus x, evaluated from y equals x to y equals 0. And plugging in, we get 1/2 x squared times e to the minus x. And so that will be the marginal density for x, assuming that x is greater than or equal to 0. And you might recognize this. This is the gamma distribution with parameters 2 and 1. Okay, so next thing we have to do is to figure out the, marginal parameters 3 and 1, because this is 3 minus 1. Okay, then we have to find the conditional distribution of y given this. So the conditional distribution of y given capital X equals x will be equal to the joint density divided by the marginal density, 1 over x squared e to the minus x. And so this will be equal to 2y over x squared. And the possible values of y will be, well, y has to be something between 0 and x. And so that will be the the conditional distribution of y given that capital X equals x. And just a quick check to make sure this actually is a PDF. If I integrate y over its range, 2y over x squared dy, that works out to be y squared over x squared, evaluated from x to 0. So x squared minus 0 over x squared, which actually works out to be 1. So there is the answer for part 1, 2y over x squared, and I should have circled the where it's defined also. And I can just do a quick check and integrate and verify that this is actually equal to 1. Okay, so that's the conditional distribution of y given that capital X is equal to x. Next, let's figure out the conditional distribution of x given that capital Y is equal to y. So to do this one, I first have to figure out the marginal density for y. And once again, my picture is that the function is defined in this part of the plane. And so this time, if my value of y is fixed, then the x's that I integrate over starts at x equals y and goes on to x equals infinity. So I have integral from x equals y to x equals infinity of y times e to the minus x dx. And so doing this integral, we get negative y e to the minus x, evaluated from x equals infinity to x equals y. And plugging in infinity and plugging in y, we get 0 minus negative y e to the minus y, which works out to be y times e to the minus y for any value of y. So that is the marginal density for y. And therefore, the conditional distribution of x given a value of capital Y will be equal to the joint density divided by the the marginal distribution. So that's equal to y times e to the minus x over the marginal density, y times e to the minus y. And so this is equal to e to the negative x minus y. And this is defined over here for any value of x that's bigger than y. And so that is the marginal density for x. And again, we can do a quick check to make sure this actually works. If I integrate this with respect to x from y to infinity, from x equals y to infinity of e to the negative x minus y dx, and integrate, this works out to be negative e to the minus x minus y from infinity to y. And plugging in, we get 0 minus negative 1, because when I plug in y, I get e to the 0. And so I do get 1. So that is a density function. Now this looks like a joint density, just like the other one, because there's both an x and a y in it. But in reality, it actually is a single PDF of one variable where the value of y is actually fixed. This does not change. Okay, part 3 is to find the correlation of x and y. To do the correlation, I remember that the correlation of x and y is equal to the covariance of x and y divided by the expected value, the standard deviation of x times the standard deviation of y. And the covariance is the expected value of x times y minus the expected value of x times the expected value of y divided by standard deviation of x times the standard deviation of y. So I've got a few things that I need to compute. Now the good news is that a lot of this I already have, and so there's no need to reinvent the wheel. First off, if I take a look back at my previous work, this was my distribution for x. I found that it was gamma with parameter 3 1/2. And therefore I know that the expected value of x is equal to r over lambda, and also the standard deviation of x is equal to the square root of r over lambda. And so I know the expected value of x is 3 and the standard deviation of x is square root of 3. So I've got this part here is square root of 3, and this part here is 3. Now let's take a look back at the marginal density for y, which I figured out earlier was y times e to the minus y. And I recognize this as something that is the gamma distribution once again, but this time with parameters 2 and 1. And so I know right off the bat that the expected value of y is equal to r over lambda, and the standard deviation of y is equal to square root of r over lambda. So I don't need to directly find the expected values because I know what this is. And so coming back to my formula, I know this is 2, and I know this is square root of 2. So from that previous work, I've got 4 of the 5 pieces. Now the only thing that's left is the 5th piece, the expected value of x times y. Alright, so I've got some work to do. The expected value of x times y. And once again, let me draw the picture. I'm integrating over this part of the plane. And so this will be the integral from 0 to infinity, integral from y to infinity of x times the joint PDF, y times e to the minus x, dx dy. So here's my value of y, and I integrate with respect to x. Okay, so can I do any, x times y. So the expected value of x times y times the PDF. Alright, so let's start integrating. And there's no shortcut to this except to just do it. So y squared, integral from y to infinity of x e to the minus x dx dy equals integral from 0 to infinity y squared. Alright, antiderivative of this by parts, we get negative x e to the minus x plus from infinity to y, plus the integral from y to infinity of e to the minus x dx, dy. Then integrating the second part here, we get y squared, then negative x e to the minus x, and the derivative of this is minus e to the minus x, and I evaluate from infinity to y, dy. All right, plug in infinity, I get 0. Plug in y, I get negative y e to the minus y, minus e to the minus y, dy. And so that's equal to integral from 0 to infinity. I get y cubed e to the minus y, dy, plus integral from 0 to infinity of y squared e to the minus y, dy. Now again, hypothetically, I can integrate this by parts, but I recognize that I can use a shortcut here. If I throw in a 1/6 here and a 6 there, this becomes the PDF for the gamma distribution. So I'll just mark this. This is a gamma distribution with parameters 4 and 1. And for this one, if I throw in a 1/2 and a 1/2, so 1/2 and a 2, I recognize this to be the gamma distribution with parameters 3 and 1. And so both of these integrals with these extra fractions thrown are equal to 1, so I get 6 plus 2, and so that's equal to 8. So coming back to the problem at the very top of the page, if I to compute this correlation, this is now equal to 8 minus 6, 8 minus 3 times 2, over the square root of 3 times the square root of 2. And so simplifying, I get 2 divided by the square root of 6. Okay, this is a positive correlation, and that makes sense. If the value of y is large, then the value of x, if the value of y is large, then because x has to be bigger than y, that means x also has to be large. If x is small, then that means the y-coordinate has to be small. So it makes sense that I have a positive correlation as opposed to a negative correlation.